Thank you very much, Nina. It is a great pleasure to be here and a great honor to be introducing to you our keynote speaker, Professor Barry Sanders, who is the director of the Institute for Quantum Science and Technology at the University of Calgary in Canada, and holds a 1,000 Talents Chair in the National Laboratory for Physical Sciences at the microscale at the University of Science and Technology, China. Professor Sanders received his PhD at Imperial College London. He was then a postdoctoral fellow at the Australian National University and the Universities of Queensland and Waikato. And then he was a Macquarie University professor from 1991 to 2003. Afterwards, he joined the University of Calgary as an I-Core chair and later as the Alberta Innovates Technology Futures Chair. He is very well known and distinguished for his seminal contributions to theories of quantum limited measurement, highly non-classical light, practical quantum cryptography, and optical implementations of quantum information tasks. His current research includes quantum resources and algorithms, optical and atomic implementations of quantum information tasks and protocols, and machine learning for quantum control. Professor Sanders is a fellow of the Royal Society of Canada, the Institute of Physics, the Optical Society of America, and the American Physical Society. He's also a senior fellow of the Canadian Institute for Advanced Research and the editor-in-chief of the New Journal of Physics. Professor Barry Sanders is highly regarded as the quantum mentor of the world due to his teaching and outreach activities in quantum information science in China, Iran, India, and Rwanda. So I think we are all up for a great treat. Please join me in welcoming Professor Sanders.
Okay. Testing. Mic is on? You can hear me? Okay, great. Yeah, it's a great pleasure to be here at Stony Brook. And I'm very happy to be able to talk to you about how to build a quantum computer. So I want to leave enough time at the end for questions and answers. So fortunately, some of the previous talks have prepared me well for this exposition of the topic. Some of the concepts we just heard discussed in the previous lectures. And I will mention, I'm the director of the Institute for Quantum Science and Technology at the University of Calgary. So Eden Figueroa, first speaker, was one of the alumni of our institute. I will mention I'm using short URLs throughout, so if anybody wants to get pictures or articles or anything, I'm using bit.ly and DOI. When you see the 10/, it's up to 6 characters, and so you could just, if you just make a short note, if you ever want to look anything up, you can easily just go to the doi.org site and plug it in. In this case, I'm going to talk to you about how to build a quantum computer. I wrote a short book about how to build a quantum computer. It's free, so I kind of like free everything. It's my ideology. And so that book is published by the Institute of Physics Publishing. It was a pilot for a series, and so that was made freely available. So if anybody wants to read it, it's non-technical. It was not designed for physicists or even scientists. It's supposed to cover the stuff I'm going to talk about at a basic level. Of course, it's hard to do, but that's the intention. Okay, and as you heard, I have a few affiliations. Most were mentioned, but I'm also a professor at the Raman Research Institute in India. I do have a very strong interest in outreach in the developing world, so I do spend a lot of time in various countries teaching quantum computing. So if you ever go to Central Africa or Southern India or any place like that, and you walk into quantum computing experts on the street, I might have had a role to play in that. Okay. Oh, I need the clicker. That's right. Okay, yeah, those are the 3 cities I'm based in. Over here you can see, I don't need that actually, Calgary at the top, Shanghai middle, and Bangalore at the bottom. My lab at Bangalore is just across the street from that palace. So some nice locations. Okay, I'll be talking to you about, just give some basics of computing. And it was interesting, one of the questions that came up in the last session, things about clock cycle and accepting transitions. I think it's important if we're building a quantum computer, no matter what background we are from, physics, chemistry, mathematics, anything, that ultimately this is a computer. That the quantum computer is just a computer that we can submit jobs to, and somehow quantum mechanics makes it better in some ways. And to appreciate what's going on, it's important to understand what a computer is. So I will take a little bit of time at the beginning and explain some of the basics of computers. I'm going to butcher it, so the computer scientists in the audience have to accept that I'm not going to be terribly rigorous, but I'll give you the idea. And then after I cover that, then I'll tell you the basics of quantum computing, and then I'll give an example of entanglement generation. Eden talked about entanglement generation in his talk, so I'll use some of those concepts. I'll get on to implementations, and I'll just cover how people are trying to build it, and I'll also mention the leading companies in each of the area, and you'll get an idea of how quantum computing is rapidly turning into a commercial venture, and there are products out there. Whether we should buy one or not is part of the debate we need to have today, but certainly there are a lot of companies building various implementations of quantum computers. And then I'll finish, when I get to the last slide, then I'll play a movie that I made, and that was done for LPS, Laboratory of Physical Sciences. So it was a lab, it's a lab in Maryland, and I like to make movies. You saw Eden played part of a movie I made, so I don't have time anymore, but I used to enjoy developing animations as conceptual tools. And you can see I like social media, so you can reach me in various ways. Okay, so let's just talk about what a computer is. And a computer is really just a machine that processes bits. Bits are binary digits, zeros and ones. And then the idea is that we have the bits appear as a string. You can see the 0, 1 in braces, and it's got a star on top. The star just means it's an arbitrary length of zeros and ones. And so the idea of a computer is that we just have zeros and ones going in, we have zeros and ones coming out, and then everything in between is where the processing occurs. We write algorithms to be able to do it. And then what makes it a universal computer is that it's able to do what any purpose-built computer could do. So if you built an abacus, or you built a machine that would solve differential equations or anything, then the universal computer can do those kinds of executions as well. Fortunately, in computing, we have a way of reducing problems down to decision problems. So if you want to factorize a number to find the factors, you could just ask, is 14 a factor? Is 15 a factor? Is 16 a factor? So we have a way of reducing problems down to decision problems that have yes and no or true and false answers. And this is very handy because it allows us to prove things with complexity. So we're able to, when we talk about whether a problem is hard or easy to solve, we're able to turn these kinds of mapping of strings of bits into yes and no questions, count how much time it would take to get the yes or no answer, and assign a complexity to it. And it's very handy. It's handy. Maybe I will use this lightsaber. Okay, so you can see here, in fact, in computers, if you want to study the theoretical complexity, you could even reduce it down to identity operations, like memories, and NAND, not AND operations. And then you could just do something like count the number of NANDs to answer the particular problem. So what we do in computing is we decompose. We take a problem, a decision problem, map a string of bits to one bit, true or false, and then we can count the number of NAND operations required to execute that. And this would be a circuit with NAND operations. And so, and I mean, the reason I'm going into this is because what quantum computing does, it doesn't change computing in the sense of what's computable or not computable, but it does change how hard it is or how easy it is to solve a problem. So reducing into, taking an algorithm, writing a circuit, counting Nand gates is a way to count the resources to be able to solve the problem. Now, there's a very interesting bridge into quantum computing I like. It's not so common in textbooks. But historically I'm talking about the 60s and 70s, there was a bridge to quantum computing that went through what's called reversible computing. And so in computing as we know it, you might do an AND operation, send 2 bits in and get 1 bit out. You can't reverse that. But back in the 60s and 70s, IBM was very interested in superconducting computing, and that plays a major role today, and that's one reason IBM is a key player. And so they were interested in reversible computing. And the reason for reversible computing was that it offered an opportunity to cut the heat cost. So if you want to pack more transistors on a chip, one of the big problems is generating heat along the way. So they explored reversible computing. Nowadays, reversible computing is still an interesting academic area of study, but it doesn't deliver gains in terms of making hard problems easy. So when I talk about it, it's really, I look at it as a way of a first step to understanding what quantum computing is about. So here's a decision problem. It maps a string of bits to a single bit, and then there actually is a way to convert it where you can just take the problem, add an extra bit, and it turns out that in a reversible computer, it's just about permutation gates. So it turns out that if you take a problem you solve on a regular computer, you can put it on a reversible computer and apply permutations to it and answer problems. So there's a very beautiful one-to-one map between the two. And instead of breaking it down to NAND operations, we could break it down into what's called controlled not, or controlled swap operations. This was introduced by Fredkin. This was introduced by Toffoli back in the reversible computing days. This controlled not just says if the first bit, so the bit is on a wire going from left to right, that's increasing time. If the first bit is 0 and the second bit is 0, don't do anything to the third bit. All of them don't do anything unless the first and second bits are both 1. So if the first bit's 1 and the second bit is 1, then execute the not operation. This turns out to be slightly changed, a reversible version of the NAND operation. And we could take reversible computing, break it down into these controlled not operations, count those, and then assess the complexity of reversible computing. And we discover we don't get any gain, in the sense that problems that are hard, that require an exponential number of such gates, will still do here. And if they're efficient, they require polynomial, so significant less than exponential, then there's no change. But that's the idea. Okay, and then what happens with this complexity argument? We count these number of gate operations. Then we can, there's actually what's called the complexity zoo. You can look on the internet. There's a curator, a veterinarian, and whatever. So there's people who volunteer their time for this, and they make this complexity zoo. It's very complicated. This is not complete. But the idea is that P represents problems that are easy to solve on a computer. BPP represents problems that are easy to solve if you're OK with a bounded error. So you're OK with getting the wrong answer some of the time. NP are problems that are hard to solve but easy to verify. And then X space are problems that require exponential space to solve. These are just exponential time. So there's this, what's known as, it's a complexity hierarchy. And so the goal in quantum computing is we want problems to go from harder classes into easier classes. And in particular, the factorization problem that was mentioned this morning lives inside of NP, and there's some subtleties with it, and we're able to drag that into a class that would be like BPP, but for a quantum computer. BPP stands for Bounded Error Probabilistic Polynomial, and there's BQP, which is Bounded Error Quantum Polynomial Time. And so there are quantum versions of complexity classes, and we're able to drag a problem from here into BQP, and that discovery 25 years ago by Peter Shor, who's now in mathematics at MIT, is what changed the world for us who do quantum computing. Suddenly the discovery that a quantum computer can make a hard problem into an easier one where it goes to this, the equivalent of this class on a quantum computer. So that's kind of our goal, is to make problems easy to solve. And so then the idea, and this comes back to the question earlier about state transitions. I mean, I understand the question was not about quantum states. It's about Turing machine type of states. And so ultimately, the way I think of a quantum computer is it's just a computer. It's the same thing. We still send bits in, and we can reduce it to decision problems and get a yes or no answer. But in between, we use this kind of magic of quantum information. And it's only magic because if you're trained in computer science and you think bits are the only representation of knowledge, the idea that knowledge can be represented in different ways kind of blows your mind. But once you get used to it and you realize there's a structure to it, it's not so crazy. So Eden talked about this, the 0 and the 1 logical state, and then we can kind of think of a sphere. And so on the equator represents the states that are equally likely to be 0 and 1, and higher, the different lines of latitude represent different weightings. And then around, when we go around the equator or around any point on the sphere, we're changing this weird phase relation. It just says that zeros and ones can be thought of as waves and interfere with each other. So we're able to play with that interference pattern. And once we do that, then we start, here's how I think about it. So that B is the string of zeros and ones. And so in quantum information, what we do is, instead of it being strings of zeros and ones in discrete mathematics, the information becomes basis vectors of a vector space. So we have a vector space, and then everything that's not quantum we call classical. And so classical information emerges where your information is restricted to basis vectors of that vector space, and then quantum information comes because you're able to use the whole vector space, not just the basis vectors. And that forms a Hilbert space. And then our logic operations, instead of mapping zeros and ones, are now mapping this complex vector space into elements of the complex vector space. If you use a quantum computer, you'll never see it. When we get quantum computers to work with compilers and all the rest, you'll just plug in your program, and then there'll be this subroutine that if you don't know the quantum stuff, would just look a bit mysterious. But it maps it to this vector space argument, exploits it, and brings it back. Suchi was mentioning the inverse quantum Fourier transform. That's one of those magical elements. And then here's the key point, that we can now think of these gates. I mentioned the Nand gate earlier. So we have gates. And here, this is a Hadamard gate. It takes a 0 or 1 on the north and south pole, and it maps it to a point on the equator, what I like to call the east and west pole. So it maps it to the east and west pole. There's another gate called the T gate, and this will change the phase of the 0. So in this case, you think of quantum information. The 0 state's like a wave, and the 1 state's like a wave, but you can move the wave so the peak or the trough just shifts a little bit. That's what that T gate does. And then this controlled NOT operation, this is equivalent to an XOR operation, will just leave the first bit the same and change the second bit, flip the second bit only if the first bit is 1. And so it turns out that these operations plus measurement. So in the classical world, we just think that information or knowledge is always there. We can always look at it. In the quantum world, we have to measure it. Suchi was talking a lot about the collapse of the wave function. So we have to plug in another operation, which kind of means we look at it. So in the quantum world, knowledge is different whether you're looking at it or not looking at it. But these are enough to build a universal quantum computer. So if we can make these good enough, then we can just put them together on a chip. This is what drives the dream for what's called gate-based quantum computing. We can just put these things together. This understanding back in the 90s opened the door to quantum computing. Just like in the computer world, the regular classical computer world, you make a better and better transistor or put more transistors on a chip. Here, if we can make these and put them together, we can build a quantum computer. Okay, so let me explain to you. Now I'm going to show you an example of, give you a simulation. So we heard about quantum simulation earlier. So now I'm going to do a quantum simulation of a famous thought experiment by Erwin Schrödinger. So Erwin Schrödinger and Einstein and others back in the early 20th century were really worried about quantum mechanics because, just like I said, knowledge is different if you're looking at it or not looking at it. Schrödinger posed the famous cat paradox. And so the cat paradox is that, that if you take a nuclear decay, and a nuclear decay is described quantum mechanically, and there's a poison gas that's triggered by the nuclear decay, and it kills the cat if it's decayed, if quantum mechanics tells you that the nucleus hasn't really objectively decayed or not decayed, then the sequence of events over here, that there's an alpha particle decay from a nucleus, causes a poison gas to trigger and kills the cat. Well, if this is described quantum mechanically, it's never truly in or out. It's in some superposition of decayed and not decayed. The cat's state of life and death is no longer determined. So there's a saying here in the US that the only two sure things in life are death and taxes. And Schrödinger pointed out that only taxes is sure, not even death is guaranteed. So our goal here is not to do this as a philosophical problem, but it's so 20th century to worry about the philosophy. Nowadays, we just accept it, and then the idea is, let's just think about how to turn it to quantum computing. So this 0 represents an undecayed nucleus. This 0 represents a living cat, which I've drawn over here. And then if we wait for the time that the nucleus is equally likely to have decayed and not decayed, that's just that H gate I showed you. So that H gate is our quantum computer representation of the waiting time for the Geiger counter to have a 50% probability of clicking. If the alpha particle comes out and releases the gas, it kills the cat. That's that controlled NOT or XOR operation. And then the output, when you do the calculation, is we just have a superposition of no nuclear decay, living cat, decayed nucleus, and dead cat. So I'm not addressing the philosophical problem at all, but I'm just showing you that this is, in quantum computers, this kind of weird stuff is built into our circuits. So what we're doing, on some philosophical level is really mind-blowing, and yet the point in the 21st century is not just to puzzle over the philosophy, but to say, okay, let's just accept it's true and find ways to exploit it. And then it turns out, and this is an interesting problem, back in the 90s, So Peter Shor showed that he can make factorization easy, and he also solved another problem. Before Peter Shor, there were people like Rolf Landauer at IBM who argued that quantum computing would be, should never think about it because quantum mechanics is only built to work at the atomic molecular scale or nuclear scale and not the real world. You know, one of the great things about the real world is you never need to know quantum mechanics to build a bridge or put up a building or many things. And so, but what Peter Shor pointed out is that if you take the principle of error correction. So error correction works like this. Suppose I'm talking to you and the room is noisy. And I'm talking to you using English, but I could just say zeros and ones. So if I had a message to give you 0, 1, 0, and there's a noisy room, you might hear 0, 0, and you don't know the middle value. But then what we can do is just what's called a repetition code. So instead of saying to you 0, 1, 0, I say 0, 0, 0, 1, 1, 1, 0, 0, 0. And then if one of those gets erased, then you hear 0, 0, 0, 1, 1, 0, 0, 0. You can know from majority vote that the missing one is a 1. And then you're able to decode. So Shor took that concept from information theory and said, why don't we do a similar thing there? This is not Shor's code, but I just put it up. This is a code that was developed by Andrew Steen, who's an experimental ion trapper at the University of Oxford in England. And so the idea is you just take a lot of quantum bits, 7 of them in this case, plug them through a lot of gates that I don't have time to explain, and get the output. And living here is that generalization of a repetition code. And then there's a process that will decode it. And you'll see this in the movie I'm going to play. That'll come up. But the idea is that we can use coding and decoding to protect quantum information. So the idea, even up to the early 1990s, that quantum is fragile, that the world can't be quantum, doesn't apply in our case. We're able to protect, so we can code and decode in a way that the nasty world that destroys quantumness, so probably, you know, most things in life are not quantum, but it doesn't stop us from building a quantum computer. And once we do that, then we're able to do, and this is what Shor showed, we're able to do, develop quantum algorithms. So I showed you this class, the NP, where factorization lives, and we're able to drag it over to this quantum class bounded quantum polynomial. So this is the trick, that we write these hierarchies, in this case involving both quantum and classical complexity, and if we could drag a problem from there to there, we know it's safe if we can make our quantum error correction. When I say this, this is theoretical. Experiments are not up to the point where we're able to really scale all this, and so it's at least a decade away to get that scalability. That's the dream. Actually, a lot of what we talk about today, using today's quantum computers, is we're trying to find out what we can do before all that is completely done. And so this is the dream 10 years down the road. And right now, the dream is try to find things that errors aren't so bad. And one of the ways that, one of the directions that's taken, and this came up in conversation this morning, is instead of this kind of problem, there's a quantum annealing direction. And the quantum annealing direction is really about optimization problems. So a lot of people using today's quantum computers are trying to find ways to solve optimization problems. If you do optimization, you're trying to find a minimum. This is a very nasty, in both cases, a very nasty landscape. And the idea when you do optimization, there are processes like simulated annealing. They simulate temperature, so the hot thing can hop over, the cool thing can't, and you kind of lower the effective temperature in your simulation until you find the minimum. And the hope, but there's no theoretical proof for this, so it's a hope at the moment, is that for certain optimization problems, the ability for your physical system to really behave in this way and get quantum tunneling would provide an advantage. So a lot of quantum computing work today is empirical. The idea is to search for problems where this kind of quantum tunneling instead of thermal hopping would solve an optimization problem. So that's where most of the stuff is happening now. Okay, let's get into the physical implementation. And so one of the ones I like, and Eden talked about a lot this morning, is about light. And so I'm just gonna, in this slide, I'm just giving you a concept of how light can be quantum information. This single rail encoding would be saying that light can exist or not exist, just like the dead or live cat. So if you don't have light, it's a 0. If you do have light, it's a 1. Turns out that this is a very complicated one to manipulate. Interesting, but complicated. There's the much more practical dual rail encoding that's used a lot now. And that's saying, if light is in the upper fiber or in the lower fiber, that's the 1 and 0. And then if we can make light use a half-silvered mirror, a beam splitter, light can go down both paths. I think Eden had the picture up. That was quantum something go both ways or whatever. Yeah, so light can go both ways. But we can do other things. There's polarization. You know, when you wear Polaroid sunglasses and you put another one in front and rotate, it blocks the light. And so that takes advantage of polarization. So whether the light's oriented this way or this way can give us 0 and 1. And this is used a lot in the quantum cryptography. And this is early and late. So in this case, you can think of light in a superposition of arriving at 2 different times. So arriving early or late, or a superposition of both, is another kind of quantum information. So it's like if you have to go to a party and you're going to show up later on time. In the quantum world, you can do both. You can be late and on time. So that's it. And then there's more interesting things where you get light can behave like a corkscrew. And if it behaves like a corkscrew, you can go beyond 0 and 1 to 0, 1, 2, or higher order logic. Okay, then if we want to manipulate it, then the elements are very basic. This is the beam splitter. Light comes in, and some of it goes through, and some of it reflects. That takes light and makes it a superposition of this way and this way. That becomes the 0 and 1. We can shift the phase. I mentioned earlier that 0 and 1 are like waves, and I mentioned that T-gate, where we shift the phase of the wave. If we shift the phase of the wave, practically we can do it a number of ways. One is an acoustic absorber. There's a quartz crystal up here, and so we're able to just kind of vibrate or use sound to shift the light a bit. We can get phase shifts. This represents something we need. I think we need to do it, but it's actually very hard. This is a picture produced in my own group, and this is the idea that this is rubidium gas in an optical cell. So it's a bunch of atoms. Atoms, the electron can live at various levels. And so if we drive it, if we hit it with light that will cause the atom to fluoresce or electron changes in a certain way, we're able then to get one bit of light change the phase of another bit of light. And so this would be wonderful if we could do it. I know in Eden's lab here, this is one of the targets. It's been a dream for many years, and it's extremely challenging to do, but it could work. I mean, it just takes more research to figure it out. Meanwhile, there's another direction, and I know this is a complicated circuit, but there's another way that instead of doing this in a deterministic way, there's a non-deterministic way called Heraldon. So it works randomly, but we know when it worked. There's other tricks on how to circumvent it. So we have a lot of problems in what we face and very clever things. Actually, I've been around the field for 25 years since it started, and one thing I know is that every time somebody comes up with a good idea, somebody comes up and says, it'll never work, and then some genius comes along and finds some way to circumvent it. So one of the fun things about the field is there are always reasons to believe it's impossible, and then there's always people coming along realizing that it is possible. It's fun that way. Okay, so in another direction, I forgot to tell you. Yeah, I put up, so these are a couple of the leading companies in the field, PsiQ or PsiQuantum, which is Oakland or Palo Alto, I'm not sure which one now, but it's in the Bay Area in California. Xanadu is a company in Toronto. And so those two companies are investing in doing light-based quantum computing. Here with trapped ions, there's a couple of companies here, AQT in Austria and IonQ, which is based in Maryland, College Park, or near College Park, Maryland. And the idea of an ion trap is you get a bunch of atoms, trap them inside an electric field. The atoms are charged, so you rip an electron off. The atom is then charged, and then they live in this region. They live in the trap, and each ion serves as a bit, a 0 or 1, but a quantum 0 or 1. And I showed you in the earlier slide the electron levels, so electrons can take various levels. In the first proposal, a barium ion in the second column of the periodic table was suggested. Actual experiments are done mostly with different atoms, but it's the concept. And so if the electron is in a very low energy state, it's a 0. If the electron is in the 1 state, it's more excited. And then other levels are used to cool and read and control. So you need other lasers to control the system. And so the idea is that you just have a bunch of ions trapped, held in place by electric fields, drive them with a lot of lasers that control those level transitions, and you're able to process quantum information in that ion trap. And then down here, it turned out that the original scheme had a lot of problems. there was a later scheme that showed for calcium how to make use. So again, this is a case where it looked impossible to do that, and then some geniuses came along and dreamt up another scheme. So that's the ion trap domain. Okay, you get the idea. Trap charged atoms in electric fields, and then each charged atom is 1 bit in your register. Superconducting qubits are all the rage at the moment, so this is where a lot of the, 5 minutes, okay. And that's including the movie or before? Before, okay, good, thanks. Yeah, so then the superconducting qubit, there's a lot of companies. D-Wave, which has been around since 1999, they build themselves as the world's oldest startup. IBM, I told you back in the 80s they were into superconducting. They've got back into it for quantum computing. Google AI. This is Alibaba Cloud. You heard that I have a job. I have jobs at different places in the world. I also have a position in China. That's where Alibaba's investing. So I get a front row seat watching this development taking place. Rigetti, as a Canadian, I'm happy to say he's Canadian, but he's based in California. So that's a Bay Area company building superconducting quantum computing. This is a picture of the IBM quantum experience that you can access on the cloud. And the idea is this looks complicated, but it's really just an artificial atom. In this case, after doing all this work, you can think of the electron as being on the left or right. So if it's on the left, it's a 0. On the right, it's a 1. But it can be in a superposition of being on the left or right. In this case, which underpins the D-Wave type technology, a flux qubit, you can think of a supercurrent going around this way or this way. And if a current goes around in a circle, it creates a magnetic field up. Goes the other way, magnetic field is down. So in this case, instead of the electron position being the quantum information, this is whether the magnetic field points up or down. So in this case, for D-Wave, the quantum bit is really a magnet that's in a superposition of pointing north or south. Okay, and then this leads me to the movie I want to play for you. And in this movie, just point out, this is the idea of working with semiconductors. I only know of 2 companies. Maybe there's more out there. This is Silicon Quantum Computing. This is based in Sydney, Australia. So Australia is investing, for many years, has invested heavily in silicon, partly because this paper that came out in Nature in 1998 by Bruce Kane, who's now in Maryland at Laboratory of Physical Science, but he was a postdoc at UNSW, University of New South Wales at the time, proposed the semiconductor-based quantum computing, and then Australia loved the fact that he was local and suggested it, and then Australia for 21 years has been investing. So that's the company launched last year, just a few months ago, to build silicon-based one. And the only other one I know is Origin Quantum, which is based in Hefei in China. And so they're doing it, but I don't know much about what they're up to. So that's the idea. This is a quantum dot approach, where you can make, again, artificial atom, and then whether the electron goes left or right becomes the basics of the quantum information. And then over here, this is the representation that the University of New South Wales is showing. So what I'm going to show you now, so if I can get switched over to the movie. So what I'll do here, I'm going to show you a movie that I made. So I'll tell you the story first briefly. I like to make animated movies. I got no time anymore, but I used to like it as a hobby. And so this one, the story was that silicon-based quantum computing was running into major challenges because the milestones weren't being met. So the technology was going well. And the problem was, how do you present at the White House in 15 minutes the story that can lead to, say, $100 million scale funding, and the people making the decision don't know quantum computing? And so I got to be part of the conversation because I like to communicate, make movies, et cetera. And so it was interesting, and I said, well, okay, just give me $50,000 and I'll make you a 4-minute movie that will help communicate what it is you're trying to do. And then I took months off my regular work. So I didn't pocket any of it. It's not for me. But it was just to pay technical people to produce it, and the idea was to try to convey. The movie's not perfect, but it does give you a flavor of what's going on. So I'm going to play, but I'm going to pause as I go. So I need the room darkened a bit. Okay, so some of it's hard to see in the light. Thank you. Okay, so here the idea is this is 15 years ago. The idea was to look at quantum computing in silicon. And of course, we're motivating it. You understand, if the NSA is involved, then they want to break codes. And actually, if anybody takes spare time and read what Snowden's leaks were about, it addresses some of these issues. Very interesting. Okay, so crack a 2048-bit number. A computer would take millions of years. For a quantum computer, it takes only minutes. So that's one of the driving forces for early funding. Here you're seeing a big chip. This is all classical, But down here, the QC is the quantum chip. Physicists in the audience will recognize the serial number. And then we dive into the quantum chip. And down here, we keep going, all the electronics to control it. And then at this level, every blue dot is a phosphorus ion. So what we have over here, each of these is a phosphorus ion. Remember I showed you the ion trap? So these are phosphorus ions. So it's effectively a giant ion trap. All the space in between is reserved for the control mechanisms, and they're actually spaced out. We worked out the calculations. All this is needed to dissipate the heat. So we looked at estimates of how much heat would be generated, and we have to spread these things out to allow the heat to get away. Now we're going to zoom into one of the blue dots. And so over here, this is the phosphorus nucleus. This is the electron cloud, an s orbital. And this crystal structure you see is the silicon. And one of the interesting issues is that, the quantum information will be the spin of that electron, whether it's spin up or down. That's the magnetic flux I showed you for like D wave. Same kind of idea. Is the magnetic field up or down for the electron? And then what happens is the electron cloud is so big that it actually encompasses quite a few silicon in the crystal. This is a major stability problem because vibrating, the noise or phonons, noise in the system, will affect the electron cloud. But that's the idea. So we just see what's going on. This moon that manifested itself is going to keep track of the spin of the electron. That's that sphere I showed you before, 0 at the top, 1 at the bottom. There's a magnetic field that appeared, and that allowed the 0 and 1 states to be different. And now, using an AC magnetic field going across, we're able to control the spin of the electron, make it point where we want. This, for experts, this is a rotating frame. You can see a frame and a rotation, so it's kind of a joke. And then we're controlling what's going on. And in the right rotating frame, the electron spin is going round and round. But you saw a flash of light here, and you'll see another flash of light now. So, darn. There was a flash of light. So the flash of light is turns out that when the electron's going round and round, it should always be 0, but we can't stop it. It's always going to precess. So remember the old days, for those old enough to remember disco dancing, and there's a disco bulb on the floor? John Travolta, Saturday Night, whatever, So the idea is that when you go disco dancing and you dance, it's periodic. You just see frozen bodies. So this is the same idea. There's a strobe light on that's showing that everything in this quantum computer have to be timed. So while all this complicated dynamics is taking place, we have to freeze at the moment that there's a 0. Now we want to control the system. And so the way that we control it is we apply an electric field. Turns out magnetic fields are global, but electric fields are local. So if we control how much time the electron cloud, how much overlap of the electron cloud with the nucleus, technically that's hyperfine splitting, we're able then to control the electron and make it veer off that great circle in another direction. And if we can take it through controlling the electric field, you see here, it hit the equator. That's that H gate, equal superposition of 0 and 1. Unfortunately, all the other electrons have to remain in the 0 state, so we have a second moon to keep track, making sure that this goes to the equator and all the rest of the electrons go back. So there's a lot of control issues to think about. Now here, this is showing how to make that controlled knot operation, the one that killed the cat. Remember, the gas was released, the cat's killed, otherwise no. This is showing how to realize that gate as a sequence of 8 steps with 2 neighboring phosphorus atoms. These are control systems that are just wires. These are wires as they look under a scanning tunneling microscope, and they're just affecting how much time the electron spends in the nucleus. So that sequence of gates then does the controlled knot operation. In there you see the cycle. This is the readout phase, so I think I better pause to explain the readout. So what happened here was, so what happens over here, I told you that we can't just do the gates. The cycle has to include the readout, the measurement. I had one of those measurement gates. Did I go too far back? Oh, darn. Sorry. I think I'll just let it play out again because it's too hard to get to the right spot. Yeah, so you see those operations. And so after this, remember, you're watching the cloud distort, but it's the spin of the electron flying around in that cloud. That's really where the quantum information is. Then the readout phase is we have to read whether the electron in the end, for some phosphorus, is which way it's spinning. And over here, this is, we have a nano-Schottky reservoir and a single electron transistor. So what happened was the electron got to here through a coherent transport process. This is a single electron transistor, nano-Schottky diode, and it's all set up so we'll only get in there if the spin is up and not if it's down. That's the idea. Then remember I showed you the quantum error correction. So this quantum error correction, this is the one I told you about the repetition code. So over here, what you're seeing are 48 steps with 28 quantum bits. And in fact, when we designed this, then the people who designed it filed a patent. So we delayed the release of the movie a few months for a patent filing because of that sequence was seen to have intellectual property value. And so this is seeing that same controlled knot operation that we've seen over and over, but seeing it in the error correction space. And now you recognize those blue dots that live on the outside of these tiles. And then what was the point of the whole thing? It was to crack a number. So it turns out that to break a 2048-bit number, which is believed to be secure now, the Shor algorithm will generally get the wrong answer, but it'll get the answer 1 time in 4 for that kind of point. So this 4 represents 4 guesses to solve the factorization problem to break a 2048-bit code. This is the guess, and now we'll see if it breaks the code. So a movie should have a climax, an ending, and we'll see if it's happy or unhappy. And over here comes the guess, and there's the code, and it cracked the code. So that makes it a happy ending because that makes the money come through. So that was what I produced. This is the creative team. These are the advisors that help. Austin Fowler at the top. He's now a Google engineer. He joined the Google team. 3 at the bottom are at the University of Melbourne. And then this is Bob Clark, who at the time was the director of the Australian program. And then he became the chief scientist in Australia for defense. And Glenn McWright was at the Laboratory for Physical Sciences. That's in Maryland. Okay, turn on the lights, please. Okay, so that's 12 years ago. Okay, so now you know how to build a quantum computer. I hope I left enough time for questions and answers, but you can go home and build it. You just have to decide which material to use. You have to decide how to do your error correction. You got to make sure you have very good control mechanisms. And you have to decide whether you can do quantum annealing or gate-based or whatever. But once you make those choices, it's fine. So mission accomplished. Thank you.
Emilio Mendez from Brookhaven and Stony Brook University. Would you like to comment on other schemes for implementing a quantum computer beyond superconductivity or quantum dots? For instance, there is a lot of interest in topological states.
Yeah, right. Yeah, I didn't discuss. Right, so then I mentioned, but because of limited time and the challenge of conveying the topological quantum computing, I didn't touch on it. That's the Microsoft bet. So Microsoft is investing in quantum computing. There are labs in Europe that are using Majorana fermions, which are manifested as the interface between semiconductor and superconductor. The way my take on it is that I mentioned the quantum error correction problem. And I said that nowadays, the quantum annealing, a lot of the push now, NISQ, so Preskill's term, noisy intermediate scale quantum computing. These are about saying, okay, error correction's hard. Let's find ways to use a quantum computer today that can still deliver something useful. Then the quantum error correction I mentioned is a long-term strategy, but the argument is that if we use topological protection, then it means that we might not need quantum error correction or not need as much. It's a little bit dangerous argument because if we do get an error, it's also protected. So we're protected against errors, but they could occur, and if they do occur, it's hard to get rid of them. But yeah, the point there is that, like I mentioned, quantum bits as being localized, an ion or a photon pulse or superconductor is localized. On the other hand, with the topological, it becomes global. So some extended defect can be the quantum bit, and then they have to do these braiding operations. So they have to take the quantum bit, and then the gates are done by braiding. So it's a very different implementation. To my knowledge, we haven't seen solid evidence of a coherent braiding operation yet, and it looks technically hard, but it is an area that's promising, and it is where the Microsoft investment is.
Somebody over here? Oh, so sorry.
So Mary Bishai, Brookhaven Lab. So I'm a particle physicist, and very naive. But somewhere I was reading about muon qubits. So, could you actually comment about that? Or is it far off?
I haven't read it. I mean, here's the even my body is full of qubits, so we always have to be a little bit careful. So what I'll do is I'll take the question. I don't know the work on muon qubits. It's very intriguing. I'm wondering if it refers to muons that are trapped in atoms. Oh, it does. Okay. So instead of using the electron, you'd use a muon. I don't know what the advantage would be. But it comes down. It gives me a chance to tell you something that I deal with a lot. So as you heard in the introduction, I'm an editor of a journal, and I have to think about journal issues. And many papers come out where there's qubits for this or that. And so when I deal with quantum information related stuff, I have to say, okay, what is the requirement? Is a qubit just any two-level system, or is there some control? So then when I study it, I think, okay, I'm not going to call it a qubit unless certain criteria or desiderata are met. Is it two-level? Can we do basic gate operations? Can we prepare it in the zero state? Can we read it? So I don't know what the muon, and if you have a reference, please send it to me. I'd be interested in reading it. But I'm also careful because a lot of work comes out where people have qubits, and we need to have a threshold for a qubit before it has to meet a threshold before we're going to say, okay, let's drop everything and take that one seriously. But it is an exciting idea. I haven't heard about it.
One more question?
Hi, I'm Raf Michelli. I'm a student at the Computational Science Initiative. So it seems like in most of the implementations that I've heard of, you have qubits pretty much just arranged in a grid or something, and you can only really do entanglement between nearest neighbors. Are there any algorithms that require further entanglement, and is there any work being done to solve that problem?
Okay, so I understand what you're saying. It's not, so there's, just like in computing, there's a bus. So we have the concept of a quantum bus. I just brought this picture up because over here, this was the first ion trap scheme from 1995 by Sirac and Solar, referenced down there. And so in that case, each ion is a quantum bit, but by detuning the laser, it turns out that the ion will only accept light if it picks up or loses some rocking motion. So the set of ions form something like a crystal. It's known as a Wigner crystal. They rock back and forth. And by shining a laser here and here, then you can entangle two distant ions. And this kind of thing exists in other schemes as well. So I understand what you're saying. It depends. Now, you're probably thinking of the solid state implementations. So a typical solid state implementation is nearest neighbor entanglement, and then you have to have the ability to swap your entanglement in a way that maintains the efficiency. But I'm just mentioning to you that not every scheme has the problem. But then I think what you're asking is, if it turns out to be it's only nearest neighbor entangled, how do we then make sure that we can do broad entanglement? And this, it works. Like, you can just do, if I need to do an entangling operation between two distant qubits, I can design it so it will go through a set of swaps or other operations that will connect the two together. The danger is that we have a clock cycle in the computer. So if some things are closer and some are further, and we do that, the clock cycle changes. And this, in my opinion, one of the biggest gaps we have in quantum computing today is on the architectural level, right from compilers, the stack that will design that kind of control. So the question you're asking, I think in the next few years, as we get 50 to 100 qubit quantum computers with 100 to 1,000 gates, these kinds of things, we know how to do it, but we need to start making sure that these complicated tasks, like entangling at two different sites, could be different timescales. We have to get everything on a cycle. So the point's really important. We can do it in every case, but for me as a physicist, I'll say, yeah, we can do it. It's straightforward. We know how to do it. But then for me, with part of me now becoming a computer scientist, I'm saying this is really hard. We have to be able to execute it through the architectural stack so that everything is clocked at the right time. So it's a good question.
Do we have any more questions?
Hi, my name is Sarah, and I am a mere journalist, so I'm not really, I'm trying to communicate these ideas to regular readers, and I understand that we're still about 10 years out from developing a fully functioning quantum computer. How long do you think that will translate into the real world for non-scientists to be able to operate this in their day-to-day lives? And what can regular civilians use this for?
Okay, great. No, I appreciate it. And you being here as a journalist is great, because the idea is we have to make sure people are informed about technological developments. I'm actually trying very hard to communicate too, so I appreciate the question. And it's hard to communicate this topic. But your question about when can we expect to see it 10 years out. So I'll tell you, I've been working in the field for 25 years. And one constant I found is that every expert says it's 20 years away. 25 years ago, it was 20 years away. So if I tell you it's 20 years away, and you come back to me in 20 years, I might still say it. So that's kind of the facetious answer. The question is, what is it that's out there? So if you look at historically, 1999, IBM Almaden, Ike Chuang's experiment, 15 was factorized. So we learned in 1999 that 15 is 5 times 3. So would that count as a great achievement? Well, the answer is it computed, and it got the correct answer. So in a sense, we've had quantum computers for a long time. So we have to take the question you ask and really deconstruct and say, what is it that we're looking for? What would be the event that we would point to and say, this is the success? And this is the troubling thing. So I will claim to you that we already have quantum computers. We have the old factorization of 15. We have quantum annealers. There are companies that you can go online and use it, and they're genuinely using quantum principles, and they're giving answers. The reason that we're very careful is because the question is, and I think this is your question, is when do we expect to see a quantum computer that will solve a problem that we can't solve in another way? Is that really what you're asking? Right, and so now if we take the factorization type algorithms, they're always going to be 20 years away. I think it's going to be a constant. But then if we take the point I mentioned where it's the optimization type problem, the quantum annealing, and this is what came up in the conversation earlier today. If we're looking for optimization that will, then we're getting enough technology in place now that we can do things that we can't simulate on a regular computer. This is known as quantum supremacy. So we're reaching the point where quantum computers are doing things beyond what we can do on a classical computer. It's just they might be totally useless. So the question is really, in the next 5 years, say, can we find something that is natively useful on a quantum computer without error correction so it solves a problem better and it's not useless? And so this is really where it is. It's not when do we get scalability in quantum computers and factorize, when do we get quantum supremacy where we're able to provably solve a useless problem better, but where do we actually get a quantum computer to the point that it's useful? And the companies that are jumping in and the investors are jumping in, they're betting on the optimization space. So you look at the kind of problems they care about. Anything from pharmaceutical design to risk portfolio management. So there's a set of problems those investors are looking at, and they're willing to put some small fraction of their wealth into this in that hope. Their bets are 5-year timescale. I'm not investing, so I don't have a feeling for it, but the investors, that's what they tell me, that they feel there's a chance that in 5 years they will be able to use an optimization algorithm to solve a problem that has $1 billion return. That's the idea. I hope I obfuscated enough that you don't know what to write.
We'll take one more question. I see a hand right there. One more question.
Hi. You mentioned earlier about how, at the end of the day, you want to have a computer that kind of obscures the kind of quantum computing part of it, so that it's kind of transparent. It looks like an ordinary computer, and we can do work with it. Maybe I was thinking maybe this is one way to do it, but maybe it's actually better not to obscure these concepts and these ideas, and actually the way forward to develop algorithms which will achieve what you want, the quantum supremacy, is to expose those to expose those underlying assumptions, those quantum mechanical assumptions, so that people can kind of from the ground up build a new way to code, a new way to program. So we're not trying to, when computers first came out, it was kind of a learning curve for humanity to kind of understand how are we going to write in a way that can understand bits, 0 and 1s and translate.
So I understand the question,
Yeah.
so let me try to give you an answer. So that's very good. Yeah, I mean, this is, there's this question of being native to the particular problem. So for me, being old enough, and I dare say Seth is in the same category, like we came along, we can fight about that later. Yeah, so the point is that like when I come into it, quantum computing, all this stuff, really, it took me many years to even grasp the basic notions and struggle to even understand what other people were doing. But I see a new generation come along, including some of my own students that come in, and for them, it's obvious. They pick it up. And so I think what you're saying fits in, not obscuring the quantum, but when I speak about it, I'm speaking as a relic in the field where I learned things my way, as a quantum physicist and gradually hammered into my head computer science principles and put it together. But what you're saying, like we're hoping that this new generation that comes in and they think quantum computing is what they grow up on, they might have the way of looking at it to find the new algorithms. We certainly need a lot of help on algorithms, and there are some really clever things still coming out, but there's a mind shift that has to take place, and it's beyond, it's beyond my ability to do it, but I think that's what you're pointing to.
Okay, please join me in thanking Dr. Barry Sanders.